Hey everyone, welcome to Science in Perspective. In this episode, I'm going to be talking about the idea that gravity is maybe not a fundamental force in the universe, but actually emerges from something more fundamental. To anchor this episode, I'm going to use a paper by Daniel Carney and team. He came out with a paper in February of 2025 called On the Quantum Mechanics of Entropic Forces. So these are one of these theories that essentially posits gravity as something that is emergent. It emerges from something more fundamental. So the usual kind of running narrative for gravity, which of course comes from Einstein's general relativity, is that gravity is a fundamental force, right? You've got the four kind of fundamental forces. You got the strong nuclear force, the weak nuclear force, the electromagnetic force, and then gravitational force. And that makes gravity, kind of purely fundamental. You wouldn't expect anything to necessarily be beneath it. But what if gravity is emerging from something else? What if what we perceive as gravity, with masses attracting each other, gravitating towards each other, is coming from something else going on? That something else is what I, of course, will talk about in this episode. So Daniel Carney's paper basically takes a thermodynamic look at gravity, and this is not something that you would do if you were just working strictly within the realm of general relativity. General relativity is taking a look at gravity. It basically says gravity is a warping of this fabric of space-time, right? So you can think of the space in which we move and the time that plays out within that space as being fundamentally connected to each other, and you can kind of envision it as essentially a fabric. And if you warp the fabric, that would be like a large mass sitting in space, like Jupiter or Earth, right? Let's say a planet, and it's warping the fabric. And if another mass comes in close proximity, it would follow essentially the geodesic, or kind of the shortest path towards the larger mass. So the analogy that is often used is, you take a rubber membrane or maybe the bed sheet off your bed, you put a bowling ball in the middle, and everyone else is holding the sheet around the corners. And that depression caused by the bowling ball is now the warping of the fabric. And so if you were to take a marble and you kind of roll it, maybe this is like, Earth around the sun, for example. Earth is the marble. You roll that marble would start to essentially, quote unquote, gravitate towards the bowling ball, right? Like the Earth gravitating towards the sun. So in other words, things are attracted to each other, not really the way that Newton was necessarily thinking about it, but just because of a consequence of the geometry, and more specifically, the warping of the fabric of space-time. Large masses cause depressions. It changes the paths that things can take, and the paths that things take are what we perceive as gravitational attraction. But, for the sake of this episode, the kind of take-home message of general relativity is that it essentially sees gravity as fundamental. So there's nothing, necessarily beneath it. There's nothing more fundamental that's leading to it. It's a fundamental force. But on papers like Daniel Carney's on the quantum mechanics of entropic forces and other, what you might call entropic or emergent gravitational theories, they think something is more fundamental that's leading to gravity. Now, what might that be? Well, a good way to approach that, and an approach that quite a few theoretical physicists will take, is to look at thermodynamics. So thermodynamics, of course, is another, fundamental aspect of reality. It's played, an absolute leading role in a number of different theories and various sciences. Obviously, the theories of gases and kinetic energies, and looking at complex systems, and really anytime that you can't get all the information of what all the individual particles are doing, which is almost always the case, quite frankly, then you have to take a more statistical approach. So in other words, you might have a large body of gas, or could even be a container of liquid. I can't access via measurement the information of what every little atom or molecule is doing in that gas. So I'd have to take some kind of higher level average. And it turns out this is quite effective to think about physical systems statistically like that, or in terms of probability. Now, of course, that's not foreign to the other leading pillar of science, which is quantum mechanics. The first pillar being general relativity, the other one being quantum mechanics. And as we know, general relativity and quantum mechanics fundamentally don't get along. If you try to mix their mathematics together, it's kind of like dividing by zero. the math kind of explodes, it goes into infinity, it just doesn't really work. And that's why you have things like string theory and theories of quantum gravity that really try to bridge these two leading pillars of fundamental physics anyway. General relativity, which is our theory of gravity, and quantum mechanics, which is the theory of small things that do crazy stuff like entanglement and superposition. And if you want to learn more about that, go check out my first episode where I talk about qubits and a lot of the quantum mechanics that goes into those quantum systems. But then there's also kind of this third piece, which is thermodynamics. Now, thermodynamics is not a part of general relativity. It's wasn't really a concern in any direct sense of Einstein when he's working on this theory, because general relativity is more about the curvature, right, of space-time, the warping. It's a geometric argument that's done with, matrices, or more to the point, tensors, and it's a geometric thing, right? You think about non-Euclidean geometries and some of the surprising effects you get from that. If you take a regular Euclidean two-dimensional triangle, all the angles on the interior will equal 180, but if you bend or warp the triangle, you get angles that are less than 180. And, it's just a different way of thinking about the fundamental geometry of reality. In other words, the most immediate thing you might do is think of two-dimensional shapes like triangles. You don't think of shapes, being warped, but that warping of shape seems to be fundamental to the theory of gravity, at least from a general relativity perspective. Okay, so, what does all this have to do with getting into these, theories like Carney's and others that posit gravity being something that actually emerges from something more fundamental? Well, I said general relativity isn't dealing with thermodynamics, but if you do decide to deal with thermodynamics from a gravitational standpoint, it allows you to anchor on to some concepts that can actually lend itself to the idea of emergence. So to understand that, you should understand first that a core concept in thermodynamics is entropy. And you've probably heard of entropy before. The most kind of the casual or colloquial way to think of entropy is in terms of disorder. In fact, it was thought of as a disorder for the longest time. And that's not really wrong. In many ways, it is actually a type of disorder. So if entropy increases in a system, that system is more disordered, generally speaking. If I scramble an egg when I'm cooking it, the entropy increases because now there's more disorder in the egg, right? Things tend to decay. If you leave a piece of food out, it will rot. Our bodies get older. The universe continues to expand and take on often more disorder, right? Supernovae are going off. If you drop a mug, it breaks, right? The mug doesn't unbreak, right? Entropy moves only in one direction, as per the second law of thermodynamics, which is saying that, entropy is always going to increase in closed systems, either stay the same or more than likely increase. Just generally, we'll just say entropy keeps increasing. And so that's, that parallels the idea that things decay, things die, things dissipate, things become more disordered. Now, not everyone likes the disordered definition of entropy, and that's because technically, the true ultimate definition of entropy is actually in terms of the number of possible microstate configurations that lead to some macro state that we observe. Okay, so, I might go to some physical system that I'm measuring, I'm looking at, and I might take a note of its temperature. I might measure its temperature. And then I might look at another system, and maybe it's got the same temperature. Well, if that second system has its atoms arranged in potentially more possible configurations, but still giving that same temperature, then the first system, which maybe doesn't have as many possible configurations for its temperature, that second system has a higher entropy. So more entropy means more possible microstate configurations that map to some higher level thing that we can perceive or measure. Okay. Now that still is essentially a kind of disorder, right? Because the more possible configurations a system can take on, the more disordered it essentially is. Now there's some experimental evidence that suggests certain, crystals might, appear to be more ordered, even though their entropy is supposed to be higher. So people, and for other reasons, people don't really like the disorder argument. It's a bit of a colloquial or casual way to say it. I don't think it's too bad. I think it still is a type of disorder. But the official definition is more possible microstates that your little pieces are doing, the more possible configurations they can be in, the higher the entropy. Okay. So just generally, you might say the more disordered it is, the higher the entropy. But again, to the point, all those different configurations are corresponding to some higher level thing. They all correspond to the higher level thing that we're measuring. Okay. So it's not just a bunch of disorder, it's a bunch of disorder that corresponds to the same structure or pattern that we measure at a high level. So I hope that makes sense. So if a lot of little things can give you the same thing, that's high entropy. If only a few little things can give you the bigger the thing that you measure, that's a lower entropy. Okay. So it's a statistical thing. Now, what's interesting about that is that's kind of lends itself to the idea of emergence. So I've just been kind of alluding to this word emergence since the beginning, where I said maybe gravity emerges. What does that mean? Well, emergent phenomena are phenomena where essentially the whole is greater than the sum of its parts. So in other words, if you go to look at something and it has a pattern to it, and then you tried to pick apart the pieces to see what went into the pattern, those little pieces wouldn't look anything like the pattern you were observing. The properties at the collective level that you're observing are not found in the individual constituent pieces that went into it. Okay, so it's a very non-deterministic, non-causally connected thing. In other words, we usually think of systems, a lot of people do, traditional science, you might say, as kind of very deterministic, Newtonian. If I'm observing something here, I can peel back the layers, reverse engineer it, and see how all the little pieces made that thing I'm looking at. That's not the case with emergence. With emergence, the thing you're looking at cannot be explained by reverse engineering it and looking at what the little pieces are doing, because what the little pieces are doing are almost entirely different than what the big piece that you're looking at is doing. So as soon as you change the scale from the microstate to the macrostate, the system completely changes. So emergence is not more, it's different, even though we are looking at more collective pieces in action. So a common example would be something like starling murmurations, these birds that fly. The individual birds have very simple kind of local interaction rules, but together they aggregate together and produce something that they can only produce in combination, which are these murmurations. It kind of looks like shadows dancing across. It takes thousands of birds to produce this effect. Now, in terms of entropy, you might say if you had thousands of birds that have millions and millions of different possible configurations that they could take on, but out of all those configurations, they correspond to the shadows that you see, so a bunch of configurations corresponding to essentially a single thing you're looking at, then that would be a high entropy system, right? A lot of entropy because a lot of possible configurations, but they lend itself to the emergence of some macro, some larger scale thing that you're looking at or measuring or perceiving. So why are we talking about so thermodynamics, entropy, emergence? So now we're starting to think about how we might talk about at least emergence in terms of thermodynamics, which makes sense. But before we connect it back to gravity, I also want to say that entropy is deeply connected to the concept of information. And that's because when I say that something has higher entropy, it has more possible configurations. More possible configurations is also more uncertainty, right? Remember I said you can't go into every little individual atom or molecule and know what they're all doing. You have to do things statistically and average them out, get an average idea of what's happening. So there's a lot of uncertainty, and the more possible rearrangements something can take on, the more uncertainty there is, because you just don't know what all those specific arrangements are. Now, the reason why that has to do with information is because information can be defined as the resolution of uncertainty. Or really, you could even just say, if something has more uncertainty to it, it has a higher information content. So, for example, if you're listening to this podcast and you know everything that I'm saying already, there's not a lot of surprise there for you. So, in a sense, I'm not actually giving you a lot of information. But if some of the things I'm saying are a bit surprising or you haven't heard before, maybe you haven't heard in a long time, there's a little more surprisal to the message that I'm giving. And that would be a higher information content. It would also be more entropy, because a lot of the things you're hearing are maybe kind of uncertain to you. I'm using different words in different configurations, and you're trying to resolve that uncertainty down to essentially a set of patterns that you understand. So entropy, which comes from thermodynamics, is also related to the amount of information in a system. The more possible configurations, the more information, because there's more you can learn. And the more possible configurations, the higher the entropy, because all those configurations, at least in terms of emergence, are mapping to the same macroscopic thing you're looking at. Okay, so hopefully now you can kind of get a sense of why something like thermodynamics generally, or entropy more specifically, might assist a scientist in coming up with a theory of emergent gravity. Because thermodynamics via entropy is already giving you a way to provide a mechanism for emergence. And if you think gravity might emerge, then maybe you can kind of combine thermodynamics with general relativity, or at least Newton's theory of gravity, or some combination thereof, in order to get an emergent theory of gravity. Okay, so let's just step back and do a really quick recap. I originally said the leading theory right now of gravity comes from general relativity. And this is a theory that essentially posits that gravity is a fundamental force in nature. There's nothing below it, essentially. And what's fundamental about it is that it's a warping of the fundamental fabric of space-time. Okay, and heavier objects warp that fabric more to a greater degree, and that's what we perceive as gravity. So it's a very geometric argument, right? You use tensors, you use geometry, you kind of change the way you think about shapes and fields and all this kind of stuff in order to understand it. But we're saying that maybe gravity, like Daniel Carney and other people that come up with these emergent theories of gravity, maybe gravity is not fundamental. Maybe it comes from something else, something more fundamental. Maybe it emerges. And in order to get a handle on theories of emergence, you have to have some mechanism behind how emergence happens. And thermodynamics can help you do that, because thermodynamics, a core concept there is entropy. Entropy has to do with all the different possible configurations a system can be in. The more possible configurations, the higher the entropy. And but the more configuration something is, also the more uncertainty, so it ties itself to information. Okay, so now to kind of bring this back to gravity, how would we combine that thermodynamic emergence to something like our perception of gravity? I'll call it perception, because now we're stepping back, kind of stepping away from general relativity and saying, well, hold on, maybe general relativity is not the full story. So let's just think about our perception of gravity, because we don't really know what gravity is. Right. You could say what gravity is in terms of general relativity, but now we're going to say we don't know what gravity is because maybe it's coming from something more fundamental. So how would you connect the thermodynamics to our perception of gravity? Well, in papers like Carney's and others who do these entropic gravity theories, they often use something like the idea of a qubit. And a qubit is kind of like a quantum carrying piece of information. I mean, it comes from a lot of quantum computing. You can actually make real qubits. So usually you think of computing in terms of bits, these little switches that go on and off. A qubit can take more than just the two states, because it can have a superposition. It can also undergo entanglement. I'm not going to go into all the quantum mechanics in this episode. Go check out the first episode to get a background on that. Just think of qubits as being something that seem to be fundamental to the universe, and they seem to carry information in the most fundamental quantum way. Now, just a quick recap. We said we got general relativity. Now I'm talking about quantum mechanics. Now, those are essentially the two core pillars of physics, right? And I said they don't really work together, but that's why we have these quantum theories of gravity where you try to get them to work together. We've got this third fundamental piece as well, which you could almost argue is another pillar, which is thermodynamics, right? However, thermodynamics does lend itself quite readily to quantum mechanics, because quantum mechanics, of course, is very statistical. It's founded on probability, arguably, right? Electrons, for example, are not really, swirling around a nucleus like planets in a solar system, like in early chemistry class you might have learned. They're really these probability waves, right? These wave functions. They have a probability of being at a certain location at a certain time, but they don't have any exact definite form or location, right? As far as we know. So we think about it in terms of probability. So it's very statistical, quantum mechanics. So now we're starting to say, okay, so quantum mechanics is a pillar, General relativity is a pillar of science. They don't really work together, but maybe gravity emerges from thermodynamics, and thermodynamics is already part of quantum mechanics. So you're starting to kind of blend things together, which of course is the goal of any kind of theory of everything or grand unified theory. Because you're really trying to bring what we believe is true from general relativity into what we believe is true with quantum mechanics. Okay, but how do they do this? And more to the point, how are they saying gravity emerges from something? Well, let's deal with qubits. So qubits are these fundamental information carrying bits or pieces. Now, they might be actual physical matter in the universe, or we could kind of just think of it almost more as a mathematical abstraction now, just for the sake of theory. But, in the lab, they do create real qubits, right? They can take atoms and cool them down to extremely low temperatures, and they can take on quantum properties like superposition and entanglement with other qubits. But imagine a system, even just theoretically, of trillions and trillions or almost countless qubits working together. Because those qubits, when I say working together, they kind of start to correlate with each other. They have superposition with each other. They're entangled with each other. And you can think of all that kind of superposition and entanglement, and I dealt with this in the first episode of Science in Perspective. You can think of that as basically dramatically increasing the complexity of the system. You're getting a way more interaction. In other words, if all the qubits were completely independent and they weren't talking to each other, it would be a much simpler system. But when things interact, which is really the underlying definition of complexity, many things interacting, then the complexity explodes. And if the complexity explodes, they can take on way more possible configurations. And if they can take on way more possible configurations, the entropy is also exploding. If the entropy is exploding, the information content is exploding. Okay, so it's all connected to thermodynamics. So qubits in the universe, trillions and trillions interacting, superposition, entanglement. The uncertainty is exploding, the information is exploding, the entropy is exploding. You have way more possible configurations, and that lends itself to the idea of emergence. So maybe from an information theoretic way of thinking about things in the universe, these fundamental quantum particles or pieces or things are interacting to such an extent that there's an absolute explosion in the possible number of configurations, because again, entangled, superposition, they're all interacting with each other. And then because of that, now you have a great degree of entropy, which should lead to patterns, should lead to the macroscopic things that we observe, just like entropy does. I mean, it's not like entropy, it is entropy. Okay? So again, I'm saying that in our physical reality, we know that when things take on more configurations, they can map to the things that we observe, right? Well, statistically, the more possible configurations you have, the more you can expect there to be a pattern that you can observe, right? It's somewhat analogous to monkeys typing on a bunch of typewriters, right? You got a million monkeys typing on a million typewriters, or whatever the number is. You can expect Shakespeare to eventually pop out. That's just statistical, right? If you combine enough things together, eventually you will get patterns. You will get intelligent patterns. You will get things that we perceive. Enough monkeys with enough typewriters could, even though they're random, you have so many different possible configurations. Eventually, all the words of typing should lead to something that's actually non-random, which is like the works of Shakespeare. Okay, now it might take millions and millions of years, but it's an example that random possible configurations are going to statistically eventually lead to something that you recognize as a real pattern. Now, my argument in this episode, so that's the idea of connecting to emergence, and Carney does that and then kind of connects it to that. But my argument in this episode, the kind of my take on this, of what's really happening, is we can think of emergent gravity, at least the theory thereof, as being a statistical inevitability. In other words, if you have a system that absolutely explodes with the number of possible configurations, then it's statistically almost guaranteed to get the formation of patterns, right? Just like the monkeys on a typewriter. You're going to eventually get combinations of things that are not just completely random, or at least we humans would not call completely random. And maybe one of those things we see is what we perceive as gravity, as gravitational attraction, right? Maybe the explosion in the amount of information and possible configurations is entropically mapping to macroscopic things that we see, and maybe that's what gravity is. Maybe gravity is a statistically inevitable outgrowth of an absolute explosion in entropy and information, driven by, I guess, something like qubits or whatever the information carrying packets are fundamentally in nature. And that's not that crazy because as per the second law of thermodynamics, we expect entropy in the universe to keep being maximized. And that's the same thing as saying information should be constantly maximized. And that's the same thing as saying the amount of possible configurations you can get of physical matter, of information, should absolutely be driven to a maximization. But out of that, you will get pockets of lower entropy, which is where you get the patterns forming, statistically. Again, kind of like the monkey on a typewriter thing. It's all random in a bunch of configurations, but out of that, you'll get pockets of order. Sentences that make sense, paragraphs that make sense. Even in the random mixing, you will get pockets of order. That's what you expect as you maximize entropy. So my take on that is maybe that's what emergent gravity really is a statistical byproduct or inevitability of the explosion of information as the universe drives itself towards maximizing entropy as per the second law of thermodynamics. Now, this also kind of relates a little bit to the holographic principle, which basically, if you look at black holes, this kind of came out of string theory and black hole studies and stuff, where they say, out of everything that goes into the black hole, all the information, where does the information go? Well, maybe it's all encoded on the two-dimensional event horizon, which is the point of no return of a black hole. Kind of think of it as like a two-dimensional disk. If you've ever seen an artist's conception of a black hole, it's kind of like, where does all the information of that black hole live? Well, maybe it's encoded on a two-dimensional surface. And then you can extend that to all of reality, which says maybe the three-dimensional reality that we perceive is actually being projected from a two-dimensional surface, which might be like the surface of the entire universe. If you thought of the universe as a big balloon, maybe its two-dimensional surface is projecting our three-dimensional reality. The point that, the take-home message here is that maybe our physical reality is all informationally driven, and all that information is being projected from a lower dimensional surface. It's kind of loosely related to what we're talking about, because we're talking about things being informationally driven with these emergent gravity theories. And finally, I just want to say, with Carney's work, it lends itself to some potential experimental testing that you could do, because it should be technically possible to see if you could detect subtle gravitational effects at the quantum level. This would probably be done with, maybe low temperature quantum systems. It might be done with some type of interferometry. I don't know if anybody knows for sure. The paper does outline some potential experiments that could be done. But imagine doing something with qubits or something in a quantum system and then being able to detect gravitational changes. That might help you make the connection experimentally between quantum systems like we talked about and the emergence of gravity itself, right? It would actually be a type of experimental evidence for the emergence of gravity. All right, that's all I wanted to say in this episode. So I thought it's cool. We usually think, just a really quick recap, we usually think of gravity as being a fundamental force. There doesn't seem to be anything below that. But maybe gravity is not fundamental. Maybe it actually emerges from something even more fundamental than it. And that's when you get into these emergent theories of gravity. And one way to approach that is through thermodynamics, because thermodynamics really lends itself to the idea of emergence because it deals with configurations at a microscopic level, mapping or corresponding to things at the macroscopic level that we actually perceive and measure. And that's similar to the idea of, remember those starling murmurations, right? You might have thousands and thousands of birds that are doing something. Those birds are kind of like, quote unquote, the microscopic level. But out of all those configurations, they produce something that we actually perceive as the murmuration, right? So it lends itself to emergence, and it lends itself to entropy, which lends itself to information. And then you go from information to qubits, and maybe all the qubits are exploding the entropy, exploding the information in the universe. And out of that, you're getting the emergence of something like gravity. Now, of course, the paper is making that connection more explicitly, connecting it to ideas somewhat to GR, but definitely to like Newtonian ideas of gravity. But my take on this is, without getting into all that, I think that it might make sense that gravity could be emergent as a statistical inevitability of the universe driving towards increased information content. Monkeys on the typewriter. If you have enough micro configurations, statistically you're going to get the formation of patterns that make sense, that we perceive, and maybe one of those patterns are gravity. It's a way of thinking about it. And again, I just related it briefly and slightly to the idea of holographic principles, the holographic principle, and then finally to some experimental evidence that might be there. Okay, so that is the core episode for this episode of Science in Perspective. For premium members, I'm going to continue this conversation. So if you like this kind of stuff, you get to hear the rest of this conversation as I go on and do a little more conversation about it. So if this is the type of thing that you like and you want to hear more, then go ahead and become a premium member. You can do that over at scienceinperspective.com, science-in-perspective.com. If you just become a member, you can do that for free, and you get access to visual concept summaries of the episodes. There's a forum on there. You can take a look at, you can get the transcripts of the episodes and a bunch of other stuff that just kind of helps you with your learning journey. But you can also become a premium member, and that gives you access to the additional high quality content, such as me continuing the conversation in each episode. So I did the core episode. That's the core episode. You all get that for free. All members get that. And if you become a member at scienceinperspective.com, you can get access to a bunch of stuff. But if you become a premium member, you get to hear the rest of this conversation. And that'll be the case for all episodes. So go ahead and check out, become a member, and maybe become a premium member as well if this type of learning is for you. And just really quickly, going off on this, you don't just get more of the conversation on the core episodes. You also get other premium content, techniques to help you learn this type of science, mindsets to help you, develop mental frameworks that help you really learn science like this on a regular basis. So a bunch of other premium content as well for premium members. Okay, so for the regular listeners, I hope you enjoyed that, and I will meet you next time on the next episode. And for premium members, keep listening and continue to listen to this conversation. Okay, so let's think about some other areas where we see this pattern. Now, this pattern, the core pattern I'm talking about, as per my take, is this, again, gravity emerging as its